Again, so this is the equation that we're trying to figure out. So the problem actually gave us the concentration of carbon dioxide, the concentration of the hydrogen, the concentration of the water as a product, and the Kc. And it's asking us to get the concentration of the carbon monoxide. So we have four inputs, and they are asking us for the fifth one. To do this, we have first to start with writing out our main formula. Kc equal to concentration of products over reactants. Products here over reactants, concentration of CO2, and there is no coefficient, so all the numbers will not be to the power of anything. And then here, so this is it. But now you need to rearrange your equation to keep the CO, this one here, in one side and everything else in the other side. To do so, we will do it this way. So we can say that CO equal to, so we'll get rid of the H2O, so we put it down here. If we put it down to this side, then we need to put it down to that side. So Kc and then H2O. And then to get rid of these two, we have to multiply here so they can cancel out each other. But if you put them on this side, then you have to put them on the other side to the top. So times CO2 times H2. That's it. The hard part here is just to organize your equation. After this, you just apply your number right away with no problem at all. So you can say here the Kc is 0.11 times, I'm just applying the numbers, 0.25 times 80 divided by 0.50 mole. All of these are m's. Equal, let's see how much is it. First of all, before we go get the result, Kc here is 0.011. What do you think, sorry, which would the product will be more than the reactants, or the reactants will be more than the products, and why? So pause the video, think about it, and then replay the video. So here you can say that Kc is equal 0.11, which is less than 1, which means that you have small Kc, which means that you have actually more reactants than products. So let's see what are the results. So here, all of the problem here, and you will get 0.044. Another study check. For each Kc, indicate whether the reaction mixture at equilibrium contain mostly reactants or products. So here is the reaction, and the Kc is equal to this number, and for this reaction is equal to this number. This one is bigger than 1. This one is smaller than 1. When it's bigger than 1, then you have more products than reactants. When you have a smaller than 1, it's 108, bigger than 1, but it's 10 to the power of minus 7. So you have more reactants in the concentration. Study check number 2. At equilibrium, this reaction, the Kc is this, and if you look to the Kc here, it's bigger than 1 here, but it's -2. So don't let this trick you. So here you will have also, it's a smaller Kc or equilibrium constant, and then you will have more reactants than products. But here the equation is not asking about this. It's asking about the concentration of this PCl5 at equilibrium. So to figure this out, and of course it's telling you that the concentration of chlorine is the same as the concentration of PCl3. So let's try to do it here. Yep. So this is number 1, number 2 here. PCl5, and then PCl3 plus Cl2, and the Kc is equal to 4 point whatever times 10 to the power of -2. And the concentration of PCl3 equal to the chlorine equal to 10 mole, 0.10 mole. So to figure out this, you can say that Kc is equal to product over reactants divided by products over reactants concentration. We don't have any coefficients, so there are no powers here. And then again, the hardest part is to put this in one side on the top. So you can rearrange your equation to be PCl5 will be equal to PCl3 times Cl2 divided by Kc. So you can say that this is equal to 0.10 times 0.10 divided by 4.2 times 10 to the power of -2. And then this will equal to, you do it on your calculator and find the numbers. So here you see it's 0.24 mole. So that's all about these types of problems. You basically, what you're gonna do is that you just set up your equation, make sure your equation is balanced, and then write your original Kc formula, and then apply your numbers. That's it. The other topic that we will be talking about is Le Chatlier principle. Le Chatlier principle states that when a stress is placed on a reaction at equilibrium, the system responds by changing the rate of forward or reverse reaction in the direction that relieves the stress. So if there is a stress, reaction has to relieve this stress. That's all. So that's what you need to understand from Le Chatelier principle. Whenever the reaction get under stress, the reaction has to release this stress. Example here. So, for example, this is both of these tank are at equilibrium. Tank A and tank B is at equilibrium. Here we add more stress in tank 1. So the thing is, you will find out that the reaction need at the end to reach stability again or equilibrium again, no matter what. So A has to be equal to B, basically. So what will happen here is that forward reaction will start going faster than the reverse reaction to get rid of the extra water here until they reach the equilibrium. Okay, that's the main idea. It's the same principle for when people go hiking, and sometimes they actually get what we call hypoxia. It happens at the high altitude where the oxygen concentration is very low. So this is the hemoglobin. So this is the equation. This is the hemoglobin, and this is the oxygen, and this is the oxygen attached to the hemoglobin, or what we call oxygen hemoglobin. So when this is low, what will happen is the stress here is releasing less of this. So to happen, the reverse reaction has to be higher, so they can actually break down the oxygen, release oxygen, so you can actually feel better this way. Uh, okay. So this is the reverse reaction. Okay. Factors that can change equilibrium. All of these factors, we'll study them. 10 factors that they actually change the equilibrium. If you add a reactant or remove a reactant, if you add a product or remove a product, if you increase the temperature in endothermic or decrease the temperature in endothermic, if you increase the temperature in exothermic or decrease the temperature in exothermic reaction, if you add catalyst, if you change the volume of the container, all of these will consider a stress on the equilibrium. And all of these, the reaction has to have action to release the the stress. So for example, adding a reactant. So here this equation is H2 plus I2 and give you 2HI. And here the stress they did is to add more hydrogen. So when you add more hydrogen, the reaction has to react to reduce this stress. So what will happen is to get rid of the extra hydrogen, the forward reaction need to be to increase. So the more hydrogen you add it will attract it to the iodine to form 2HI and then get rid of the extra hydrogen from here. So the reaction will shift towards the product. Forward reaction will increase, and or you can say that the reaction will shift towards the product. Let's try here. Removing reactants. So if we remove the hydrogen, by removing the hydrogen from here, you apply the stress. So the reaction needs to relieve this stress and release some hydrogen. To release some hydrogen, then the reverse reaction has to increase, so they can actually, the HI can be broken down into hydrogen and replace the removed hydrogen. So here you can say that the reverse reaction is is increasing, or you can also say that the equilibrium shifts towards reactants. Adding a product. If you add a product here, means that you apply stress. So adding product, you need to get rid of this product. To get rid of this product, then the reverse reaction will increase and the equilibrium will shift towards the reactants. If you remove a product, removing a product means that you apply the stress, and to get more HI, then the forward reaction has to increase, and the equilibrium shifts to